Hello and welcome to the latest webinar by BYK-Gardner. My name is John Kowalski. I'm part of the marketing team here as always, and I'd like to welcome you. Today's topic is dispersing and milling for battery and fuel cells. Couple housekeeping things. We are recording this, so immediately following the presentation, you will receive a link. Feel free to watch it later, share it with colleagues, grab some screenshots. Also, if you think of any questions after the fact, you can hit reply to those automated marketing messages and it'll come to my team and we will route that to the appropriate technical specialist in your area. Also, during the presentation, if you do have some questions, please jot them down in the chat box. That should be located in the bottom right-hand corner of your screen. Time permitting, we will get to them. If for some reason we do run out of time, we'll follow up with you directly on that. So I think that's it. Our speaker today, Mr. Andy Stumer, he is the director of our VMA-Getzmann North America business here at BYK-Gardner and all things dispersion and milling. Andy, how are you, sir?
I'm doing great. Thank you, John.
All right. It's all yours.
Okay. Thank you, everybody, for attending our webinar today. And we're just going to go do a quick overview, talk about the flow of the presentation. So we're going to just go do a quick introduction of the business, and then we're going to go into the dispersion and milling process overview. So we're going to discuss it in more detail, what actually happens when we're dispersing, and some of the key points. We're going to cover those, and then we're also going to dive into the different types of equipment that is being used to produce these products. And we're also going to cover some of the laboratory capabilities that we offer at our sister company, BYK USA in Wallingford. We have a really nice high-end dispersion lab where you can actually come in and try out that type of equipment. And you can see right there on the introduction slide, the VMA-Getzmann product line for dispersing these types of material covers everything from basically small laboratory scale dissolvers and milling systems all the way up to pilot and manufacturing. So we really cover the entire range, and we'll talk in more detail when we cover the different types of equipments that are being used for this process. With that, so VMA is the manufacturer of this equipment. It's a German company. They are based in Reichshof, which is about 30 miles east of Cologne, kind of in the center of Germany. The company was founded in 1972. The beautiful couple that you can see right there on the top right, Hermann and Elke Getzmann. Hermann founded that business almost over 50 years ago, and it's still in family hands. The company is now run by his two children, Christian and Martin Getzmann. And Hermann still comes into the company about once a week just to follow up with everybody and make sure that they are still following his design philosophy of the Dispermats. And the relationship with BYK-Gardner goes all the way back to 1988. So since that time, we have had the exclusive distribution rights here for the United States as well as Canada. The company, as I said, is still in family hands. They have about 100 employees worldwide, including their agents. And VMA-Getzmann is known for making state-of-the-art dissolvers, different types of milling systems, such as vertical bead mills, basket mills, again, for laboratory pilot as well as manufacturing spaces. And that Dispermat right there, the first actual model that came onto the market was in 1973. It's an older unit right there, the first one, but 50 years old. And actually, we have some customers that are still running on the original motors today, believe it or not. So these units will last a very long time. And the motor technology is really, really state of the art with that direct drive mechanism. It doesn't really require a lot of maintenance. They will really last for a very long time. Okay, so with that, when we talk about dispersing and milling, obviously there's a lot of different end-use markets, and the newer one, or one of the latest end-use markets where this type of equipment is being successfully used is actually in the battery development arena, as well as fuel cells. You know, we have some customers that develop these fuel cells now with the iridium oxide, milling down these components, using diplomats to do that. And of course, all the startups and battery companies now that need that type of equipment are also using diplomats to disperse these different formulations for the electrolytes, as well as the different barrier coatings. As you can see on the slide right here, they're used for many different types of battery sort of formulations. Silicon, to the electrodes, silicon oxides, lithium, you name it. There's many more actually, because this is an ever expanding market in industry, and there is basically new formulations coming up almost every day. I was at the battery show not too long ago up in Detroit, Michigan. It's pretty amazing when you talk to these companies about the state of the battery development cycle today, and how far it's come along, and all the different technologies that are being used to produce these awesome batteries. So with that, so again, if you look at right there, that main building right there in the middle is actually the core center of VMA. They have added on another section in the rear. It's actually a creek that flows right by the property, and that portion in that building in the middle, the additional floor that they added on, and that building in the rear is actually the design center and also manufacturing space where they actually produce these diplomats. VMA is known to produce, obviously, a lot of different custom machines. So about 40% of everything that they build or design is based on customer requirements. And again, everything from laboratory scale all the way up to production is really designed right there. So with that, let's go right into the dispersion process, what actually happens when we are dispersing. So we start out with these larger particle clusters. They're called agglomerates. So basically, these are these smaller particles that are fused together by these invisible binding forces, these Van der Waals forces that are holding these particles together. And when we're dealing with larger clusters, we call them agglomerates. And basically, what we want to do is we want to break up these binding forces and turn them to aggregates. And then ideally, we want to go and reduce them further down to the primary particle size. So that's really what we're doing when we're dispersing materials. So we're also wetting them, and then we try to stabilize them once we broke up these binding forces and separate these particles. It's important that we stabilize our formulation to keep them in a suspended state so they don't flocculate back together. And of course, some of you are pretty familiar with the big additives product portfolio. They have different products for these type of stabilization processes. So this slide here kind of lays it out more visually, I think, from the dispersion process point of view. So we always start out with a dissolver using a cowl's blade or an immersion impeller, some people call it. That's a blade with teeth. And we're putting in energy, high tip speed, and then basically we're wetting our material and then we are breaking up these agglomerates and turning them into aggregates. Once we reach about 10 to 30 microns of particle size is when we actually start the fine grinding or milling process. You can see there is a rotor right there. That would be the second step in the dispersion process, and then we're able to go to really fine particle size, down to actually the primary particle size. Some people like to go down to 100 nanometers and lower, depending on what you're trying to do. And that's what you need is a rotor or a milling system. And then again, you need to stabilize these products so they don't flocculate back together. So here's an example of how a cathode is being, produced with using a dispermat. In this case, we are using a vacuum system to take out any type of air. Some people actually have a separate port that they use to flush it with argon or nitrogen gas, so any inert gas, during the dispersion process. And then here the different raw materials we're putting in, the PVDF, the NMP, and then of course the active material that's being added in carbon black to then basically disperse the material. So that here is actually using a TMS sensor, which stands for torque measurement system. It actually measures the torque on the shaft in real time. It's not a calculated value, it's actually measured to give the user real-time data on with respect to the change in viscosity. That's what the TMS sensor does. So it's actually really precise measurement telling you on the display exactly how the material is behaving and what happens to the viscosity during the dispersion process. All the data obviously can be stored and then sent over to a spreadsheet to create lab reports and so on. There's also the ability to capture the data and look at the entire process in a graphical form. So you have a diagram on the display that will give you a trend line for each of these critical dispersion values, like your energy input, the RPM, the tip speed, your temperature, and of course your torque value, and then showing you those values in a trend line. And then you can actually see what is happening during the dispersing process in real time. If you step away from the unit, you'll be able to come back later and actually look at these lines and say, hey, we had a spike here. How is the process going? Are we properly dispersing our material? And you should see, that you're creating more surface area. So the amount of energy you will be using would then actually show up in the trend line, and you can actually see progress being made during the dispersing process. So basically, here is a close-up of the control panel. We then proceeded on to actually mill the product. We used, in this case, an immersion mill or a TML basket mill, and that was carbon black. You can see there are cooling jackets right there. It's really critical to always the temperature in check when you're especially milling. You're putting a lot of energy. Energy translates into heat. So we really need to keep an eye on that, and temperature control is critical. And you see here on this picture, we actually have temperature control of our basket mill. You see these two jackets right there on the shaft of the unit. That's actually the mill head right there that's immersed in the container. And right above it, we have these bars that are actually holding the mill head. They are hollow, and there's actually cooling channels that go in, and that would actually provide the cooling fluid to ensure that we maintain the appropriate temperature. In addition to that, we also want to cool the supply vessel or the working container, which is actually double-walled, jacketed. You can see only the output of the of the coolant. There is another one that's not visible on this picture where actually you are feeding the coolant into the container. So you are maintaining appropriate cooling for both the mill head as well as the container, which is really, really important. And then again, with that milling system, you can see here, this is another example of the efficiency of a basket mill. So we pre-dispersed this material. There was an LIP cathode slurry, and we actually pre-dispersed for about 30 minutes. We started with 100 microns of particle size, and we milled that down for about 30 minutes, then using a TML, and we were able to go down to 2 microns on average particle size with a standard TML basket mill. So really efficient and very quick to actually reduce the particle size by just using one system, a dissolver, and then the additional basket mill attachment that goes right on it, and we're able to accomplish that in a very short time. Okay, so here is actually a better photo of the TMS, or integrated torque measurement system, that I spoke about earlier. That's really important to monitor the real-time viscosity. So normally when you look at the Dispermat or a dissolver, the torque value is a calculated value through the frequency inverter. And that's just basically a calculation. And it can drift depending on what the RPM range is and how much energy you're putting in. So it's not a very precise value. It just gives you some idea of what is happening. Now with the TMS sensor, we are now able to really dive into the change in viscosity and give you a very accurate measurement of 0.01 Newton meters, which is roughly transit about 10 centipoise increments. So that is a really helpful tool to get that good understanding of what is actually happening there with the viscosity. And so these values are then displayed on the actual control panel. So you can see that. You can also record that data. And then it also helps you to obviously precisely calculate any viscosity shifts that are happening during the dispersion process, especially if you want to upscale that to pilot or manufacturing. The repeatability is obviously excellent, as well as the reproducibility, because it's truly a measured value and not calculated. So there is no input with the frequency inverter at all. So we have our own separate sensor. It's plugged in right to the shaft right there. And then obviously the data is displayed again on the control panel. So it's a really good development tool. A lot of our customers that are purchasing this also use it to then get a good understanding of how the product would behave when they scale it up. And you can also acquire a TMS sensor for the production scale units that we offer, where then you can also see the change in viscosity while you're actually making your slurries. Okay, so important to understand, the dispersion process itself is always 2 steps. We start out obviously with the pre-dispersion process, where we are using a standard dissolver. That again is just basically a shaft with a cowl's blade. And then we want to aim for about 18 to 25 meters per second of optimum tip speed. That's the ideal dispersion window or pre-dispersion window. And that's when we are really breaking up these van der Waals forces and starting to reduce these larger agglomerate particle clusters down to the aggregate level. Now, as I mentioned earlier, when you're about 10 to 30 microns of particle size, then the cowl's blade no longer is efficient enough to continue to further reduce the particle size. So we need something that gives us more energy and more power to really now break down these aggregates and turn them into primary particle size. So for that, we need a milling system. So there are different types of milling systems on the market that are being used for that type of development work. So we are looking at vertical bead mills. Some people call them pop mills, which are really good for R&D environments, but they're not really scalable because we would need a lot of beads and the handling is complicated the larger you go. So for small volumes like a quart or less, they're really, really good. Very easy to handle, quick to clean, and very good milling performance and results. Then there are these basket mills or immersion mills that are very popular. They're gaining a lot of traction over the last few years. And they are really good because you can use them in the laboratory and then scale them up, staying within the immersion milling system family all the way up to production. We're going to cover those in more detail some slides down, and then also the horizontal media mills that a lot of you folks probably are familiar with. We're a horizontal bead mill using a rotor and then obviously your ceramic beads to either circulate through or pass through the mill, and we'll talk a little bit more in detail about that milling system as well. Okay, so when we are starting out with a dissolver, it all comes down to picking the right container size for our volume, and then obviously we want to select the right dissolver blade ratio to our container. So there is not one blade that can be used for all the volume. So we really have to look at the viscosity of our product, the product volume, and that helps us then pick or select the right size or diameter dispersion blade. So just for example, if you were taking a 1000 milliliter or 1 liter container, you can see on that chart here on the right that we would be able to use a 30 millimeter blade and also all the way up to 70 millimeter blades. So anything in between would be suitable depending on the viscosity that we are dealing with, right? So the low viscosity range, we want to reduce our blade diameter, so it's like 500 centipoise or less. You want to really use the smaller one, like 30 to 40 millimeter. If my viscosity is anywhere between 5,000 and let's say 5,000 centipoise, more medium viscosity, then we can increase the diameter of our blade. About 60 would be ideal. And then if we're dealing with very thick materials, almost like pasty products, then we want to increase the diameter of our blade to achieve a proper pre-dispersion. So that's important. And we also have that particular slide on our website, that table, so you can actually review that later when you are running your product to make sure you're picking the right blade size, respective to your container. Okay, the other critical part is the tip speed. As I mentioned earlier, we're aiming for about 18 to 25 meters per second of peripheral speed. And the calculation there is pretty simple. So all we want to do is take the speed of our rotor, the RPMs. We multiply that by 3.14 and then multiply that with by the diameter of our blade. But because we are expressing that in meters per second, we need to also express the blade in meters. So let's say you're using a 50 millimeter blade, then you would express it with 0.05. So let's say we're doing 1000 RPMs, for example, times 3.14, and then times 0.05 for that 50 millimeter blade, and we divide everything by 60, that would actually give us the tip speed for a 50 millimeter blade at 1000 RPMs. And so that's how the actual tip speed is calculated. Now, on all of our newer models, the Dispermat CV3 Evo, the new lab model, as well as all the other ones, the new CN, and of course the AE, which is our flagship model, they will now automatically calculate the tape speed for you, so you don't have to do it anymore. There'll be actually a window that you can open up, and then you just type in or dial in the diameter of your dispersion blade that you'll be using, and then it automatically calculates it for you depending on the RPMs that you're running. So you don't have to actually do that anymore. But if you're using older dissolvers and you have to do it manually, then that would be actual the calculation to figure that out. Okay, we have another really important cue here. It's the donut effect. It's called that because when you are optimizing your dispersion process and you're in the right viscosity range, then you actually should be seeing a donut that would appear inside of the container. And it actually does look like a donut. You can see that right there on this picture. And the dispersion process, the deagglomeration, is actually taking place right on the edges of our blade where the teeth are located. And that happens on top of our blade as well as on the bottom of our blade, since we also have teeth that are pointing downwards. And we would also be able to deagglomerate in that area as well. That's actually a better picture here where you can see it. The material would hit the tip of the blade, these teeth. The blade is spinning again about 18 to 25 meters per second to be in the ideal tip speed window. And then the teeth would really break up these binding forces and reduce these larger particle clusters to the smaller aggregate clusters. Okay, so we have a couple examples here. So in this case, we have a material where we are actually putting in 21, we're running with 21 meters per second of tip speed. We're putting in about 850 watts of energy. So we would call that an optimized dissolver batch. And you can see here, we actually are looking at a beautifully shaped donut. So pre-dispersion process looks good. Tape speed is right, and we're actually seeing the formation of our donut. That's what we actually want to see. Now, there's going to be cases where obviously a donut doesn't form, but you're still pre-dispersing. That would be if you're dealing with viscosities that are very low. That obviously would mean that the donut wouldn't be able to form because it would automatically collapse as soon as it's trying to form because your viscosity is very low. So ideally, anywhere between 2,000 to 5,000 centipoise is really an optimum viscosity range for that donut to show up. But again, low viscosities, difficult to get the donut, doesn't mean you're not actually pre-dispersing. It's just that visual cue is missing. And then also, if you're dealing with formulations that are very thick, more like pasty products, then also you won't really see a donut because the material is so thick it won't be able to form, but doesn't mean you're not actually breaking up particle size. Okay, just keep that in mind. So there are a few things that we want to look at to optimize our dispersion results. So obviously the duration of our pre-dispersion process. We're looking there about 15 to 30 minutes, in some cases maybe 45 minutes, but that's really the longest I've ever seen. We want to ideally have a donut effect, but if we don't see it again, it could be viscosity related. Tip speed, again, 18 to 25 meters per second, ideal tip speed window. Geometric consideration, so that ratio container size and blade relative to the different viscosities. So that's really important that we pick the right blade diameter. And then obviously there's different types of blades on the market, and picking the right blade for your formulation is also critical. The amount of mill base, we recommend about a 50% fill rate. You can go up as high as 70% and as low as 40, but 50 is really ideal. We know when you put in the energy and the tip speed, the product raises up, and then you will probably spill the material over the lip of the container. So it's important to always have a cover and don't overfill the container more than 70%, and you would really have an issue. Then obviously our concentration, our formula, what does that look like? We want to keep the temperature in check. Again, temperature control is very important, especially when we are milling. We're putting in a lot of energy, and we really got to keep that temperature in check. So we want to always make sure that we keep the temperature on the lower side so we don't overheat our product. Also, when we're dealing with solvents, it's somewhat of a risk. So we don't want to definitely go above a certain temperature threshold. So our Dispermat also offers the ability to basically put in or program cutoff values. That basically ensures that the dissolver would not exceed a certain temperature. So you could program that, let's say 80 C would be your maximum desired temperature. You can program it to give you a warning at 70 C, and then a second warning, let's say at 75 C. And then once it reaches 80 C, it would either power off, or you could program it to run with a different tip speed or RPM, or actually different energy input. You can also run the Dispermat with the amount of energy you're putting in, and that way the machine will automatically then adjust the tip speed. If you're locking in a certain amount of wattage, then the machine would either increase or decrease the tip speed depending on your change in viscosity. So you can also program that in the cutoff values to ensure that you're not overheating your materials. And then again, the Big USA has an excellent additive portfolio. They will help you to better wet out your materials, improve the dispersion process, and then again, keep these particles in a suspended state, because we don't want to do all this work and then we end up exactly at the same place where we started. So very important to have a good dispersing agent in our formula. And then once we stabilize everything and we want to go and further reduce our particle size, is when we're actually starting the second step in the process, which is our milling cycle. And we can see here, obviously, we'll be able to put in a lot more energy with the rotor and the beads. We are further deagglomerating our particles down to below micron range into the nano range. Some people go below 100 nanometers. We have actually one customer that went down all the way to 50 nanometers with the right setup, using a nano kit and very fine beads. And that basically allows us to really break down to those particles, giving us, of course, improved product characteristics, smallest possible particle size, and then ideal particle size distribution. That obviously all needs to then measured on a particle size analyzer. Grind gauge won't help you there anymore. These are super small particles. So there is obviously technology that will give you those results. But also important to remember here is that you can't really forego the dissolver stage. It's very important to always properly pre-disperse and make sure everything is wetted out and deagglomerated before you actually start the milling process. If people just mix things together and think, okay, I can put everything into my horizontal bead mill, there is an agitator that's in the supply vessel that won't do a good job mixing, you're going to probably end up with a clogged screen or a clogged dynamic gap. And then you won't be able to circulate your product through the mill, and you're going to be ending up cleaning it out and causing more work for yourself than you would have had if you had done a good job properly pre-dispersing the material. Okay, so when we talk about the bead milling process, we want to really understand what is happening actually inside of a bead mill. So we have a rotor or a milling disc inside of a closed chamber. And there, of course, with an immersion wheel, we have an opening on top and on the bottom, but where our beads are located, it's kind of in the center of our basket. And on with our horizontal mills, obviously, we have a milling chamber, and that's where our beads are located. Now, as these beads collide towards each other and drift towards each other at very high velocities, the actually shearing or breaking up of our aggregate clusters actually takes place right as the beads collide in that triangle. When you put two beads together, there's this triangle being formed, and then basically that's where you're pushing away the aggregate particles, and they're being reduced to these smaller particles. Kind of like the example with the rubber duck when you were a little kid in the bathtub and your parents gave you a rubber duck to play with, and you were trying to catch the rubber duck with your hands, clapping your hands together, and it's very difficult to get a hold of that rubber duck. It's always being pushed away by these forces of your hands clapping together, and that's kind of like also what's happening inside of a bead mill. So think of these beads as your hands and the particles cluster as a rubber duck, and as you're clapping your hands, these particles create these forces, these shear forces actually breaking up these binding forces and reducing the particle size. So that's really what's happening. Of course, there is also going to be some impact shearing where you're going to end up having a particle cluster right in the middle of beads, two colliding beads, and that obviously would crush those particles and also reduce them to smaller sizes. That's called the impact grinding effect. But by probability or normally, this would not happen because, again, because of the fluid dynamics, these particles will get pushed away and broke up. These binding forces will break up that way through the shearing motion. Okay, so that's kind of what happens inside of a bead mill. And now there was also an important aspect is to maximize the kinetic energy. And a lot of that comes from the weight of our beads. So we want to really look at selecting high quality, heavy beads. Of course, they can't be metal. Most battery applications, you don't want the iron deposited inside of your mill base or slurry. So we would use ceramic beads, either zirconium oxide or yttrium stabilized, just a few of those examples. And then as you can see, if we're using glass beads, for example, you're dealing with relatively lightweight bead, and the specific weight compared to 2.5 to 6.1 on the zirconium oxide bead, right? So the zirconium bead is obviously much heavier, so that would also give you more kinetic energy, would translates then also into higher milling performance or better milling performance, because we really want to get as much energy introduced into our grinding process as possible. Hardness is also really important there because we are milling with these beads. There's potential when they collide that there could be sharding or breaking up, especially when we're dealing glass beads. So they have a hardness of 400 versus almost 1200 for a zirconium oxide bead. So they're much harder. So the wear is going to be much lower on a ceramic bead versus a glass bead. So you ideally want to always pick ceramic bead over glass, just for the stability, for the weight, and overall milling performance. There is different bead sizes, of course. So depending on how small you want to go, Again, you always want to start out with a larger bead size. So, for example, most applications call for about a 1 to 1.2 millimeter standard bead size. That's when you're in the range of 10 to 30 microns. And then as we are progressively milling down our material and we're getting smaller particle size and one near particle size distribution, then we are able to actually change out our beads and use smaller beads and go progressively smaller. So we actually offering now beads that are even smaller than 0.4. We actually now offer beads where you can find them on the market that are as small as 0.1 millimeters for super small nanoparticles. And our milling systems are capable of handling these beads. So you would have to acquire like a nano kit and that be then the right platform to really get these super, super small particle size. We see that a lot with the development of these different types of barrier coatings. Solid state batteries come into mind here, where they are calling for super, super small particle size. And they would then use relatively small beads, 0.2, 0.3, or maybe even smaller for these type of applications. But again, keep in mind, bead quality, bead performance, very, very important when you are selecting the right bead. Okay, so here are some of the critical parameters that are influencing our milling process. So the particle size, again, 10 to 30 microns after our pre-dispersion process is ideal to then guide us right to the milling process. Bead size, again, select the right size of beads, start out with about 1 to 1.2 millimeters, and then work your way down until you get to the right particle size. And if you want to go smaller and you're not seeing any more particle size reduction, then maybe it's a good time to then reduce the size of your beads. Of course, that then you would also change the screen out, use a smaller screen or a smaller dynamic gap like on the horizontal mills that we offer. Again, the weight of the beads, very important. The bead volume, so different milling systems have different bead loading ratios. So depending on what you're running, and of course, the size of your milling chamber. So there's always a right ratio. The shape of the beads, also very important, especially customers that are using glass beads. You really got to screen them. They do short and they wear unevenly. So you see under the microscope, if you were to look at them after extended milling cycles and you don't screen them, you're ending up with very odd bead shapes. Sometimes they're not even round anymore. They're like more oval in shape. They're shards. So that's usually really a problem with the glass beads. You don't see that as much with the ceramic beads, but you still should keep an eye out and then possibly screen them and get rid of the ones that are wearing down quicker. When we are milling versus this just pre-dispersing, we're actually running with a lower tip speed. So again, pre-dispersing 18 to 25 meters per second optimum. By milling, we are reducing the rotor speed down to 10 all the way up to 16 meters per second, which is the preferred tip speed window for the milling cycle. Product temperature, again, here when we are milling, even more critical to keep it in check. When we are using just a callus plate for pre-dispersion, depending again on the viscosity, but it's not as big of a problem. Temperature doesn't tend to rise as fast or quickly as when we are milling. Now, excuse me, now when you're milling, temperature tends to go up very rapidly. So we really have to make sure cooling is in place. Select the right quality chiller. With that, I also let customers know there's a question about what kind of chiller do you recommend. So we tell our customers that you should have enough chilling power on the chiller to match the output of the motor on the disper mat or on your mill. So if you're running, let's say the maximum output of a mill is, let's say, 1 kilowatt of motor power, then the chiller should also be able to have an output of 1 kilowatt. So that's kind of like the worst case scenario. If your mat is using all that power available, then you would definitely want to match that and have the ability to not only match it, but maybe even go a little beyond that on with your chilling system to optimize the cooling process and ensure that there is no heat buildup that the chiller couldn't handle. So always look at the output of the disper mat, the kilowatt output, and match it up to the chiller. Never buy chillers that have less motor power or output than the actual dissolver. Milling time, there is no real rule there. You mill until you're done. Particle size that you desire is achieved. So we have seen anywhere from 30 minutes of milling time all the way to 6-8 hours. Again, depending on really your formulation and how small you want to mill. So ceramic-based coatings tend to, where you're looking for like sub 100 nanometers, they tend to require much longer milling time. So there we have seen, different, milling cycles with various bead sizes. So you start out with 1 to 1.2 millimeter beads, mill for an hour, hour and a half, 2 hours. When you're looking at the results and you see, okay, the last half hour, we're really not getting any more particle size reduction. Okay, at that point, then you want to change out the bead size, go smaller, and that way then you are targeting the right particle size, and then you basically run another milling cycle. So that really can add up depending on how small you want to go. Then depending on the setup, there are different residence times of your material inside of the milling chamber. Of course, if you are running an immersion mill like a basket mill, that timing is different than on a horizontal mill. You have much more, but you have more cycles through an immersion mill or a basket mill than you would have through a horizontal medium mill. The viscosity of the mill base, very important. We want to make sure that the product flows. If you have a formulation where it's like thick as a paste, it's very difficult to actually mill this material. It won't go through our mill, and you need to have, in that case, a different type of setup, something like a plunger system that we also offer. We're actually pushing the material with force through the actual milling chamber with pressure. And then again, a type of bead mill is very important, whether you have a basket mill, as you can see right here, or a horizontal bead mill, or that vertical bead mill, that pot mill I spoke about earlier. So let's take a look at the basket mill or immersion mill, which is gaining a lot of traction with battery companies. Really good milling results, very efficient, able to go down to about 500 nanometers without any problems. So what you have here is basically a basket, stainless steel in the standard configuration. But for battery application, we highly recommend that is actually outfitted with ceramic insert. So the milling chamber will be zirconium or silicon carbide or any other material that you so choose. We do a lot of custom design for these type of applications. And then obviously the milling disc or rotor would also be ceramic. You can see the milling chamber then gets filled with beads and then submerged into our container, where then the milling disc would spin at high velocities, And then we would have a screen on the bottom of our basket mill, actually ensuring that the beads stay inside of our basket mill and only the mill base or product can actually flow through it, the material. And then right below it on the outside, we have a pulse blade or a dispersion blade, not to disperse, but rather to actually pump the material outside of the basket through the screen and then push it around to the top of our basket mill, where then it gets sucked back into the basket. So you have a very good rotation in and out of a basket, good flow of our mill base. So a lot of cycles are possible with the basket mill. So what helps us is that patented pumping wheel design that we have on our TML basket mill. So there's actually on top of our milling disc, there is another smaller disc that has basically fins on top. They look like shark fins, and they're actually designed to create a vortex at high velocities to actually really suck the material into our basket mill. And then, of course, the beads will do the job with the milling disc, really breaking up these particle size clusters and over time reducing the particle size. So another key advantage of the basket mill over the horizontal mill design is cleaning. Very, very easy to clean compared to horizontal bead mill. So once we are done milling, we just basically pump out our material, or we remove the container, replace it with another container with cleaning agent, and then we submerge our basket mill into, and if you're using solvent, obviously the solvent bath, and then we run it again for a few minutes so that the solvent really can do a good job cleaning the internals of our mill as well as the beads at the same time. If you want to do a fine cleaning, there is a couple screws on the bottom, these Allen screws that you remove, and then you're basically able to remove the screen, and then the beads would drop out. You can catch the beads in like a pan on the bottom, and then basically clean them with the sonic bath that always works well, and then do the fine cleaning, the fine touching of the components once you open it up. But it's relatively easy. There is really no high-end wear parts. So there is no leaking. There are no seals really. So the immersion mill is very user-friendly compared to a horizontal medium mill, and extremely effective. Okay, so that's another picture, close up actually on the bottom right there. You can see the basket mill layout with that disc on top and those fins. And then obviously our cooling channels in the double walled basket mill wall for optimum cooling of our mill base. Very, very important. Great system. The APS, again, a pop mill, excellent tool for R&D, very easy to use. So you have two containers. The top containers would hold your slurry. You are replacing the cowls blade on the dissolver shaft with the milling disc, in this case, a double milling impeller. You add your beads to your slurry, you close it up and run it in a closed system. Once the milling cycle is completed, just open up the drain plug on the bottom, and then you hook up an air hose into the, there is a socket in the cover that's embedded right there, and that basically allows you to pressurize the top vessel and then force your milled material into the container below. Now that can also be fitted with all ceramic for the battery or fuel cell application. We don't want any iron deposited. So a lot of companies that are processing the iridium oxide for the fuel cell are actually using that system. You can go up to 7 liters. It's extremely expensive raw material. And so 7 liters is quite a bit of volume. And that's what they are using to process those radium oxide slurries. Here's just the drawing of the APS. So you can see the milling impeller, the beads, the slurry, the drain plug. And then once you remove the drain plug, you're forcing out the milled material into the container right below. Extremely efficient, awesome, but not ideal for scale up because you can add 100% bead loading. So let's say you have a 1 liter container, you have 500 milliliters of material. You can also add 500 milliliters of beads. Now imagine if you were to produce 2,000 liters, you'd have 2 tons of beads, and that'd be prohibitively expensive, also extremely hard to handle. So this type of milling system is an excellent tool for R&D and small pilot, but not really for manufacturing. Okay, we call that APS, the air pressure system. Again, very fast milling, the bead ratio very high, ceramic capability. It's got its own shaft sealing system, so you can pressurize it. Different screen sizes are available, so you can also choose between the size of media you want to use. And then with the air regulator, the air pressure regulator, you're actually able then to dose the right amount of air you need to purge out your mill base depending on the viscosity. And again, super easy to clean, very easy to handle, but not suitable for upscale or manufacturing. Then we have the horizontal bead mills. We have the SL for our laboratory scale applications. And then we have the horizontal bead mill for manufacturing, which we call the RS. Very, very efficient systems. We have them with nano kits. We have them in full ceramic. We have complete non-metal versions with PTE. We have actually some customers that have gold-plated components, titanium rotors, and so on. That actually keeps any type of ferrous metals outside of our milling process to ensure that there is no cross-contamination. So here, again, supply vessel with a motor and an agitator and a pumping system, allowing us to put the product through the milling chamber and then circle it back around to the top, where then we can actually cycle our material and mill for a very long time until we achieve the desired particle size. Really, really nice horizontal bead mill design. Anybody that has one actually is really happy with them. You can either pass through or do recirculation method. Our system has that integrated pumping and steering system. The machine, the lab unit can go all the way up to 6,000 RPM, giving you that optimum tip speed from 10 to 16 meters per second. We can control the rotor independent from our pumping speed. Again, for ceramic, for battery application, different linings and milling rotors. Materials are available. Different milling media size, now actually 0.1 for the nano, and all the way up to 0.3. And we can also cross convert our standard SL over to an SL nano. So you have that capability of doing that with our machine instead of having to buy a brand new one. For lab applications, I just want to touch quickly on the new CV3 Evo we introduced this year. Excellent lab dissolver that has the ability to be actually fitted with either an APS milling system or a basket mill and even a vacuum system. You can also mill under vacuum. So this is an excellent companion at a relatively low price and cost point to do everything you really need to do in your lab to produce your battery slurries or your fuel cell products, and then scale them up. All the data on the screen gives you excellent upscaling, numbers that you can store and then log and create lab reports and everything else. We also got a unit with vacuum or non-vacuum if you don't need it, with the actual torque measurement sensor. And then we also offer the vacuum unit with the scraper system. So for very thick materials, you want the container wall always scraped in that way. All the materials being properly dispersed and pushed into the center of the unit where then the blade will take over. Again, scaling is key. You also want to then be able to scale that up. In this case, a little larger unit, we can go all the way up to production. And that here has the scraper unit installed and also the ability to add a nitrogen purging valve or any type of inert gas you want to push through, create a blanket. That's possible with these higher end models. Again, control capability is there, creating lab reports and so on. Here, quickly, the philosophy behind the Dispermat. Mr. Getzmann was always keen on providing a solution that was used or could be used for many different applications. So when you buy a Dispermat, you're not only buying a dissolver, you're actually buying a tool that you can use for many different applications. So by buying a different accessory, you're able to convert it very quickly to a rotor stator, to a vacuum system, to a basket mill, the TML. We can add a wall scraper or use it as a vertical bead mill. The air pressure system or APS are all extra add-ons that you can purchase at a later date, and they will always fit on to our Dispermat. We have that quick change system that allows you then to very quickly go in between these accessories. It'll take you less than 1 minute to convert a dissolver over to a basket mill or add a vacuum system. So extremely user-friendly, and it's a great tool for lab as well as manufacturing applications. And with that, thank you again. I went 2 minutes over, but we also have that great lab space in Wallingford, at BIC USA, where we can host you, run your materials, show you the capabilities of the equipment, and tie in our BIC Additives colleagues. They're experts on selecting the right dispersant agents or wetting agent for your battery or fuel cell application, and then work with our Dispermats to produce those results you are looking for.
Great. Thank you, Andy. Thank you, everyone, for joining us. Again, if you have questions after the fact, hit reply to any of the marketing messages, and we'll funnel it to Andy and his team. Thank you. Have a great rest of your day, and we look forward to seeing you on future BYK-Gardner webinars. Thank you.
Still a few people on the call here. Just want to mention we do have some stock right now of our CV3 Evo. Very rare that we actually have stock. So if you're looking for something to close out before the holidays, you have ended your budget, we do have a laboratory scale machine, and we do have one SL50 for pilot lab and pilot applications, a horizontal medium mill that was actually built for a battery customer that unfortunately went out of business. It's brand new. It's built with all the right materials, not to cross-contaminate your battery slurry, and then it actually produced the product very efficiently. So if you're interested, please shoot us an email. We'll be glad to send you some documentation and show you that unit. If you are interested, let us know. With that, thank you again for your time today.